Beneath the surface of every ocean on Earth, a shadow war continues to unfold in complete silence, while nations broadcast their military might through impressive displays of aircraft carriers, fighter jets, and tank formations. The most lethal weapons in modern warfare remain completely invisible to the human eye, operating in a realm where sunlight never penetrates and where the slightest sound can mean the difference between mission success and catastrophic failure. Submarines represent humanity's most sophisticated attempt to weaponize stealth itself, transforming the ocean depths into hunting grounds where vessels worth billions of dollars stalk one another in a deadly game of three-dimensional chess that plays out across thousands of miles of underwater terrain. The concept of underwater warfare predates modern technology by centuries. Born from humanity's eternal desire to strike without being struck, to observe without being observed, and to control strategic waterways without revealing one's position or intentions. The earliest recorded attempts at submarine warfare can be traced back to ancient times, when divers would attempt to bore holes in enemy ship hulls or attach explosive devices beneath the waterline. However, the first serious attempts at creating submersible vessels capable of sustained underwater operations emerged during the Renaissance period, when inventors and military engineers began to understand the fundamental principles of buoyancy, control, and underwater navigation. Leonardo da Vinci, whose notebooks contained designs for everything from flying machines to siege engines, also sketched plans for a submersible vessel that could theoretically operate beneath the surface of water while maintaining communication with the surface world. His designs, while never constructed, demonstrated an early understanding of the ballast tank principle that would later become fundamental to all submarine operations. The Renaissance period saw numerous attempts at creating workable diving, bells, and submersible vessels, most of which failed due to the technological limitations of the era, particularly in metallurgy, sealing techniques, and air supply management. The first successful military submarine operation occurred during the American Revolutionary War, when David Bushnell's Turtle attempted to attach an explosive device to the hull of HMS Eagle in New York Harbor in 1776. While the mission ultimately failed due to the inability to penetrate the ship's copper-sheathed hull, the attempt demonstrated the psychological impact that underwater threats could have on enemy forces, the knowledge that an invisible attacker could potentially approach from beneath. The waves introduced a new dimension of vulnerability that traditional naval warfare had never previously considered. The 19th century witnessed rapid advancement in submarine technology, driven primarily by improvements in metallurgy, mechanical engineering, and the development of more reliable propulsion systems. The Confederate States Navy during the American Civil War deployed the H.L. Hunley, which became the first submarine to successfully sink an enemy warship in combat when it destroyed the USS Housatonic in Charleston Harbor in 1864. This historic achievement came at tremendous cost, as the Hunley and its entire crew were lost in the attack, highlighting the extreme dangers faced by early submarine crews, who operated vessels that were essentially death traps held together by primitive technology and desperate innovation. The Industrial Revolution provided the technological foundation necessary for the development of practical military submarines. Improvements in steel production allowed for the creation of pressure hulls capable of withstanding the immense forces exerted by deep water, while advances in mechanical engineering made possible the development of reliable ballast tank systems, periscopes, and torpedo tubes. The invention of the electric motor provided submarines with a means of propulsion that did not require air intake, allowing for extended underwater operations, while improvements in battery technology gradually extended the duration that submarines could remain submerged. The late 19th and early 20th centuries saw rapid proliferation of submarine technology among the world's major naval powers. The French Navy led early developments with the Gymnote and subsequent Naval-class submarines, while the British Royal Navy initially dismissed submarines as underhand, unfair, and damned un-English before recognizing their strategic importance and beginning rapid development of their own submarine fleet. The German Imperial Navy, constrained by British naval supremacy on the surface, invested heavily in submarine technology as a means of challenging British control of the seas through asymmetric warfare tactics. World War I marked the first large-scale deployment of submarines in strategic warfare, fundamentally changing the nature of naval combat and international maritime law. German U-boats demonstrated the devastating effectiveness of submarine warfare against both military and civilian targets, implementing unrestricted submarine warfare policies that brought neutral nations, including the United States, into the conflict. The sinking of passenger vessels such as the Lusitania revealed the indiscriminate nature of submarine warfare and its potential to escalate conflicts beyond traditional military boundaries. The technological innovations driven by World War I submarine operations established many of the fundamental principles that continue to govern submarine design and tactics today. The development of hydrophones allowed submarines to detect enemy vessels through acoustic signatures, introducing the concept of passive sonar that would later evolve into sophisticated sonar arrays capable of detecting targets at ranges measured in hundreds of miles. The introduction of deck guns gave submarines surface engagement capabilities, while improvements in torpedo technology increased both range and reliability of underwater attacks. The interwar period witnessed continued refinement of submarine technology, with major naval powers conducting extensive research into extended-range operations, improved diving depths, and enhanced stealth capabilities. The Washington Naval Treaty limitations on surface vessel construction led many nations to view submarines as cost-effective alternatives to expensive battleships and cruisers, driving innovation in submarine design and construction techniques. The development of snorkel systems allowed submarines to run diesel engines while remaining submerged at shallow depths, significantly extending their operational endurance and reducing surface exposure time. World War II represented the golden age of conventional submarine warfare, with underwater operations playing decisive roles in both the Atlantic and Pacific theaters. German U-boat campaigns against Allied shipping demonstrated the strategic impact that relatively small numbers of submarines could have on global supply chains, while American submarine operations in the Pacific systematically destroyed Japanese merchant marine capabilities and crippled the island nation's ability to supply its far-flung territories. The war drove rapid advancement in submarine technology, including improvements in torpedo guidance systems, radar detection equipment, and underwater communication methods. The Battle of the Atlantic illustrated both the potential and limitations of submarine warfare when conducted on a strategic scale. At its peak, German U-boat operations sank Allied merchant vessels faster than they could be replaced, threatening to sever the lifeline between North America and Europe that was essential for maintaining the war effort against Nazi Germany. However, the development of effective countermeasures, including improved sonar systems, coordinated convoy tactics, and dedicated anti-submarine aircraft, gradually shifted the balance against submarine forces and demonstrated the evolutionary nature of underwater warfare tactics. Pacific theater submarine operations revealed different aspects of submarine warfare capabilities, with American submarines conducting extended patrols lasting months while operating thousands of miles from their home bases. The vast distances involved in Pacific operations drove innovations in submarine endurance, navigation accuracy, and crew life support systems. American submarines also pioneered special operations capabilities, conducting reconnaissance missions, delivering supplies to resistance forces, and evacuating personnel from behind enemy lines, demonstrating the versatility of submarine platforms beyond their primary role as torpedo attack vessels. The conclusion of World War II marked a technological watershed that would fundamentally transform submarine warfare through the application of nuclear power. The capture of German submarine technology, including advanced hull designs, improved battery systems, and revolutionary air-independent propulsion concepts, provided the foundation for post-war submarine development programs. However, it was the successful adaptation of nuclear reactor technology for submarine propulsion that created a completely new category of underwater vessel with capabilities that dwarfed anything previously imagined. The USS Nautilus, launched in 1954 as the world's first nuclear-powered submarine, represented a quantum leap in submarine capabilities that can only be compared to the transition from sailing ships to steam power in surface naval warfare. Nuclear propulsion eliminated the fundamental limitation that had constrained all previous submarines: the need to surface regularly for air to run diesel engines and recharge batteries. Nuclear submarines could remain submerged for months at a time limited only by crew endurance and food supplies rather than fuel or air requirements. The strategic implications of nuclear-powered submarines became apparent during the Cold War, when these vessels evolved from tactical weapons designed to attack enemy shipping into strategic platforms capable of delivering nuclear weapons anywhere on Earth while remaining virtually undetectable. The development of submarine-launched ballistic missiles created mobile nuclear arsenals that could not be targeted by enemy first strikes, fundamentally altering the balance of nuclear deterrence and providing assured second strike capabilities that help maintain strategic stability between superpowers. The acoustic signature revolution of the 1960s and 1970s transformed submarine warfare from a primarily visual discipline into a complex acoustic environment where the ability to hear without being heard became the primary determinant of tactical advantage. The development of sophisticated passive sonar arrays allowed submarines to detect targets at ranges previously impossible, while improvements in sound dampening technology made submarines progressively quieter and more difficult to detect. This acoustic arms race drove innovations in everything from propeller design to reactor cooling systems. As submarine designers sought to minimize every possible source of detectable noise, modern submarine warfare represents the culmination of over 2 centuries of technological evolution, producing vessels that combine the stealth characteristics of their predecessors with the endurance of nuclear power, the precision of computer-guided weapon systems, and the strategic reach of intercontinental ballistic missiles. Today's submarines operate in a multi-dimensional battle space where acoustic stealth, electromagnetic signatures, thermal management, and hydrodynamic efficiency must all be optimized simultaneously to maintain tactical advantage in an environment where detection often means destruction. The evolution from David Bushnell's hand-powered turtle to modern nuclear-attack submarines represents one of the most dramatic technological progressions in military history, transforming crewed diving vessels into sophisticated platforms capable of independent global operations lasting months while maintaining complete stealth. This evolution continues today, with emerging technologies such as air-independent propulsion systems, unmanned underwater vehicles, and advanced artificial intelligence, promising to further revolutionize submarine warfare capabilities. The silent service has evolved from a desperate expedient of weaker naval powers into the dominant force projection capability of the 21st century, operating in a realm where traditional concepts of national boundaries, territorial waters, and maritime sovereignty become increasingly meaningless in the face of platforms that can appear anywhere at any time, without warning or detection. The ocean depths represent one of the most challenging environments on Earth for both human survival and technological operation. Yet it is precisely these hostile conditions that make submarines the most effective stealth platforms ever developed. Understanding why submarines are so difficult to detect requires examining the unique physical properties of the underwater environment and how submarine designers have learned to exploit these characteristics to achieve near-perfect invisibility. Unlike aircraft or surface vessels that operate in environments where multiple detection methods can be employed simultaneously, submarines operate in a realm where the fundamental laws of physics work to their advantage in remaining hidden from enemy forces. Water itself serves as both the greatest challenge and the greatest ally for submarine stealth operations. The density of seawater, approximately 800 times greater than air, creates immense pressure that increases by 1 atmosphere for every 10 meters of depth, requiring submarine hulls to be engineered as pressure vessels capable of withstanding forces that would instantly crush surface vehicles. However, this same density that makes submarine construction so challenging also provides exceptional protection against most forms of electromagnetic detection. Radio waves, radar signals, and most other electromagnetic radiation used for detection and communication cannot penetrate more than a few meters into seawater, creating a natural shield that renders submarines invisible to the vast majority of sensors used in modern warfare. The acoustic properties of the ocean environment present both opportunities and challenges for submarine stealth operations. Sound travels much more efficiently through water than through air, with acoustic waves capable of traveling thousands of miles through the ocean with minimal attenuation under the right conditions. This characteristic makes passive sonar systems extremely effective for long-range detection, allowing submarines to identify and track targets at distances far exceeding visual range. However, the same properties that make sound travel efficiently through water also mean that submarines must be engineered to minimize their acoustic signatures across multiple frequency ranges to avoid detection by increasingly sophisticated enemy sonar systems. Ocean thermal layers create natural acoustic barriers that submarine commanders can exploit to avoid detection while simultaneously hampering their own sonar capabilities. The thermocline, a layer of water where temperature changes rapidly with depth, acts as an acoustic mirror that can reflect sound waves and create shadow zones where submarines can hide from surface-based sonar systems. Experienced submarine commanders learn to navigate these thermal layers with precision, using oceanographic data to position their vessels in acoustic shadows while maintaining their own situational awareness through careful management of active and passive sonar systems. The three-dimensional nature of the underwater environment provides submarines with tactical advantages unavailable to surface vessels or aircraft, while surface ships are constrained to operate on a essentially two-dimensional plane, and aircraft operates in predictable flight patterns governed by aerodynamic limitations. Submarines can maneuver in 3 dimensions with relatively few constraints. This freedom of movement allows submarines to approach targets from unexpected angles, including from directly below, where most surface vessels have minimal sensor coverage and defensive capabilities. The ability to change depth rapidly also allows submarines to exploit different acoustic conditions at various depths, moving between thermal layers to optimize their stealth characteristics or sensor performance as tactical situations demand. Modern submarine hull design represents the culmination of decades of research into hydrodynamic efficiency and acoustic stealth. The transition from the traditional surface ship-inspired hull designs of early submarines to the streamlined, teardrop shapes of modern vessels was driven by the need to minimize both hydrodynamic drag and acoustic signatures. Every surface feature, from the sail design to the placement of control surfaces, is carefully engineered to minimize water turbulence that could create detectable noise signatures. The hull itself is constructed using specialized materials and techniques designed to absorb rather than reflect active sonar pulses, making submarines significantly more difficult to detect using traditional sonar ranging techniques. Propulsion systems represent one of the most critical aspects of submarine stealth technology, as the method used to move through water can create acoustic signatures detectable at great distances. The development of nuclear propulsion eliminated the need for submarines to surface regularly to run diesel engines. But early nuclear submarines were actually noisier than their diesel-electric predecessors due to the constant operation of reactor cooling pumps and steam turbines. Decades of refinement in nuclear propulsion technology have produced reactor systems that operate with minimal mechanical vibration, while advanced sound isolation techniques prevent machinery noise from being transmitted through the hull to the surrounding water. Propeller design has evolved from simple rotating blades to sophisticated systems engineered to minimize cavitation, the formation of vapor bubbles that collapse and create distinctive acoustic signatures detectable by passive sonar systems. Modern submarine propellers use complex blade geometries, specialized materials, and precise manufacturing tolerances to operate efficiently across a wide range of speeds while minimizing noise generation. Some advanced submarines have moved beyond traditional propeller systems entirely, employing pump jet propulsion systems that eliminate many of the acoustic signatures associated with conventional propellers while providing improved efficiency and reduced maintenance requirements. The magnetic signature of submarines presents another detection challenge that must be carefully managed through sophisticated degaussing systems and careful selection of hull materials. The Earth's magnetic field creates detectable anomalies when large metal objects pass through it, and submarines represent some of the largest moving metal structures on the planet. Advanced degaussing systems use carefully controlled electrical currents to counteract the magnetic signature of the submarine hull, making magnetic anomaly detection significantly more difficult. The placement of internal equipment and systems is also carefully planned to minimize localized magnetic disturbances that could create detectable signatures. Thermal management represents an increasingly important aspect of submarine stealth. As infrared detection systems become more sophisticated and widely deployed, nuclear submarines generate significant amounts of waste heat that must be dissipated into the surrounding water, potentially creating thermal signatures detectable by advanced sensors. Modern submarines employ sophisticated heat management systems that distributes waste heat throughout the hull and carefully control the temperature of water. Discharge from cooling systems to minimize thermal signatures. The management of engine exhaust heat when operating on the surface or at snorkel depth requires similar attention to thermal stealth characteristics. Advanced materials. Science has revolutionized submarine construction, with modern vessels incorporating sound-absorbing coatings, vibration-dampening alloys, and composite materials designed to minimize detectable signatures across multiple spectrums. Anechoic coatings applied to submarine hulls are designed to absorb active sonar pulses rather than reflecting them back to the transmitting system, significantly reducing the effective range of enemy sonar systems. These coatings must be engineered to operate effectively across a wide range of frequencies, water temperatures, and pressure conditions, while maintaining their effectiveness throughout extended deployments lasting months without maintenance. The internal arrangement of submarine systems reflects careful attention to vibration isolation and noise control, with sensitive equipment mounted on sophisticated shock absorption systems designed to prevent mechanical vibrations from being transmitted through the whole structure. Every piece of rotating machinery, from reactor coolant pumps to ventilation fans, is carefully isolated using advanced vibration dampening techniques. Even seemingly minor sources of noise, such as crew movement and equipment operation, are carefully controlled through design features such as sound-absorbing deck coverings and noise-dampening materials throughout the interior spaces. Electronic warfare capabilities have become increasingly important for submarine stealth operations, with modern vessels equipped with sophisticated systems designed to intercept, analyze, and counter enemy detection attempts. Electronic support measures allow submarines to detect enemy radar and sonar transmissions at ranges far exceeding the detection capabilities of those same systems, providing early warning of potential threats and allowing submarine commanders to take evasive action before being detected. Advanced signal processing systems can identify specific types of enemy sensors and automatically deploy appropriate countermeasures to defeat detection attempts. The concept of acoustic stealth extends beyond merely reducing noise generation to include active measures designed to confuse and mislead enemy sonar systems. Modern submarines can deploy acoustic decoys that mimic submarine signatures while the actual vessel moves to a different location, creating false targets that draw enemy attention away from the submarine's true position. Advanced signal processing systems can also generate acoustic signatures designed to mimic other types of vessels, allowing submarines to masquerade as merchant ships or other non-threatening targets when operating in areas where complete stealth is not possible. Operational stealth technique developed through decades of submarine warfare. Experience are as important as technological solutions in maintaining invisibility. Submarine commanders must understand the acoustic properties of their operating environment, including how water temperature, salinity, and depth affect sound propagation. Successful stealth operations require careful coordination between submarine speed, depth, and course to minimize acoustic signatures while maintaining tactical advantage. The timing of operations, including when to use active sonar, when to change depth, and when to alter course, can mean the difference between mission success and detection by enemy forces. The integration of artificial intelligence and machine learning systems promises to further enhance submarine stealth capabilities by automatically optimizing operational parameters to minimize detectable signatures while maintaining mission effectiveness. These systems can continuously monitor the submarine's acoustic signature and automatically adjust propulsion, maneuvering, and system operation to maintain optimal stealth characteristics. Advanced predictive algorithms can anticipate changes in ocean conditions and automatically recommend course and depth changes to maintain concealment while positioning the submarine for optimal tactical advantage. Modern submarine stealth represents the intersection of advanced materials science, sophisticated engineering, operational expertise, and cutting-edge electronic systems, working together to create platforms that can operate virtually undetected in the most challenging environment on Earth. The physics of underwater operations continues to favor stealth over detection, making submarines the most effective platforms for covert operations, strategic deterrence, and power projection in the modern era. As detection technologies continue to advance, submarine stealth systems evolve in response, maintaining the technological edge that makes these vessels the most dangerous weapons that most people will never see. Operating in silence beneath the waves where the laws of physics themselves provide the ultimate camouflage.